Natural quotients are awesome. It's been cited 2,681 times and is a part of alignment datasets like Long, LoRa, Atlas, Retro, Muppet. We use syntactic transformation to turn free trivia quotients into something about as good as NQ and looks like NQ. But why transform quotients into NQ when NQ already exists? First, NQ is expensive. While NQ quotients are free, at least to Google who collected the data, NQ does not naturally come with correct answers to the quotients. To find those answers, annotators look at the quotients and a retrieve Wikipedia page to extract the answer. This is probably quite expensive. While Google has not officially released cost, they haven't done it again, suggesting that the price is very high. Second, NQ is getting old with obsolete quotients and out-of-date answers. For example, NQ asks, when does the new season of Law and Order SVU come on? The official answer is September 27, 2017. Because this masterpiece from Dick Wolf will never end, the latest season premiered on October 3, 2024. Third, NQ is comparatively small for training LLMs with only 300k samples. Fourth, because NQ comes from real users, the questions sometimes have issues. For example, another NQ example asks how many nominations does Game of Thrones have? This question can ask about the number of nominations Game of Thrones has across all its seasons or any particular season or award ceremony. To address these issues, we investigate whether and how we can transform trivia samples into questions that resemble natural questions. We use a trivia dataset quiz pool which is pyramidal. Examples from this dataset are many sentences long. They begin with clues that are initially difficult but become progressively easier. We extract the series of clues that an expert author thought were noteworthy about an entity. We call these examples elicitations for two reasons. First, they are not grammatical questions. Second, to distinguish them from natural questions. Now we discuss the process of naturalization, converting the elicitation into multiple NQ-like questions. As a first step, we will split it into sentences. We consider each of the sentences independently. We check to see which heuristics can be applied to convert the clue sentences to the natural-like question, then apply the heuristics and correct the error of the questions after transformation. You can see the paper for all the heuristics, but we will walk through several examples from elicitations, show you the heuristics we apply, and then the final naturalized question. We will walk through an example from the elicitation about White Nile. First, we split QB elicitation by splitting them through period. The first heuristic splits the clues with a conjunction to construct two independent clauses. So if the original elicitation was, this river forms the Bujagali and Murchison Falls in its Victoria incarnation, and it also contains a segment named after Lake Albert, we can create two different questions. If there is a conjunction in the elicitation, we apply the heuristics. Here we have the conjunction and. So first, we create a dependency parse tree and identify the root verb of the sentence. In this case, forms. The subject is this river, and from the parse tree we find the object and the other verb contains, which has the subject it and the object a segment named after Lake Albert. So using the conjunction and, we create two independent clauses from the original elicitation. So after splitting, the first question is, this river forms the Bujagali and Murchison Falls in its Victoria incarnation. And second question, it contains a segment named after Lake Albert. Next, another heuristic converts our elicitation into a grammatical question. This heuristic is applied when there is no WH word. For example, from the previous heuristics, we get two independent clues. This river forms the Bujagali and Murchison Falls in its Victoria incarnation. The first is easy. We check this for the this word in the noun phrase and just replace this with which, converting it to the final question. The second clue, it contains a segment named after Lake Albert, is more difficult as it has no this in its noun phrase. So we need to find pronouns that are coherent from the desired answer and replace them with a canonical answer type. Over all the questions about White Nile, what general noun is used to refer to it? In this case, river, and replace the pronoun with which river. So the final question is, which river contains a segment named after Lake Albert. In other cases, converting imperative sentence to interrogative questions requires a little more work. This heuristic is applied when these patterns are present in the elicitation. For example, we have an elicitation for 10 points, name this river that unites with its blue counterpart as part of the longest river in the world. Our elicitation starts with the pattern, so the heuristic will be applied. To rewrite this as a grammatical question from the parse tree, for the root verb name, we find the noun and its relative clause. In this case, the verb unites is the head of the relative clause, so the object of the question is the rest of the relative clause from the verb. We merge that with the which plus canonical answer type. So the final question is which river unites with its blue counterpart as part of the longest river in the world. But this is 2024. Why are we using things like syntax trees when we could use a large language model? For comparison, we also transform elicitation into question by prompting models GPT and Llama 2. We extract clue sentence from the QB elicitation, identify the lexical answer type, and then prompt GPT and Llama 2 to produce a natural question. Here's what an example prompt looks like, and after Llama 2 conversion, we get the question. But GPT and Llama 2 transformations sometimes hallucinate some information and change the entity asked in the question. It also includes the answer in the generated question, although the prompt instructs not to. For example, the elicitation is asking about French painter Jean-Auguste Dominique Ingres. However, Llama 2 converted question asked about the significance of the position of the hands in the painting instead of the entity of the painter, and also included the answer in the question. In the next example, for the Llama 2 generated question, important clues are removed and random clues are added. Now we move into the evaluation of our dataset. The first evaluation setup is zero shot. It's as if we are in a universe where Google never released NQ and we evaluate on the NQ test set. In some ways, this is a little bit unfair to us. We have to ensure we use no NQ data. This is challenging because many zero shot QA models are based on LLMs that do not disclose training data and likely use NQ data. We have more details in the paper, but one clue is that they repeat NQ answers to question even when NQ is wrong. For example, an NQ question, who won the Oscar for Best Picture in 1976, says that the answer is Rocky. However, this is wrong. One Flew Over the Cuckoo's Nest won the 1976 Best Picture, but GPT also answers Rocky. Thus, we select two systems with high accuracy on traditional NQ training, DPR and Replug, and train them from the ground up. In red, we have natural questions. This is the upper bound. QB-Trans is our dataset where we naturalize QB elicitation. It lags behind a model trained directly on NQ by only about 6 points on average. The LLMs GPT and Llama 2 lag over by 10 points. For the second evaluation, we combine all of the natural dataset with the original NQ dataset to have the largest NQ-like dataset possible. We evaluate the systems with 4 systems. The top model in the NQ Challenge Leaderboard ReflectionNet, GenRed, DPR, Replug from the previous evaluation. This time, we are training these models with QB-Trans data along with the NQ dataset. In red, we have natural questions. Supervised training on QB NQ 100 and evaluating on the NQ test set produces the highest F1 score compared to trained only on NQ. Similarly, QB Trans and 50% of NQ reached within 7 points of the F1 score of NQ training system. But does this work for something other than our crazy elicitation? To show the generalization of our naturalization technique, we apply it to 4 different trivia datasets: Jeopardy, Trivia QA, Hotpot QA, and AI King Japanese dataset to make them all look like NQ data. For example, Jeopardy has elicitation. We apply heuristics and convert it to 2 NQ-like questions. Similarly, for Trivia QA elicitation, we apply heuristics and convert them. We apply this now massive dataset with over 1400k examples to train systems and test it on the MMLU benchmark, which consists of exam questions. We fine-tuned the LLM models such as GPT, Llama 2 with our generated dataset and saw an average accuracy improvement of 3 points. These 2 experiments point to the generalizability of our dataset in both settings. Our naturalization can be applied to non-NQ data and our transform data can answer non-NQ data. To sum it up, this is a cheap and easy way to build on the efforts of the trivia community to create something that's nearly as good as Google's finest. Moreover, this can serve as a continuous flow of new natural questions even with the absence of new NQ test set. The size of the transform dataset is manifold larger than NQ. For future work, we can apply this conversion technique to other languages probing dataset. Second, it can be used where NQ is a part of alignment dataset. It can also be used to create adversarial dataset